This is Galileo's Gaff. After initially saying infinities could not be compared, he then compared them and decided they are all the same. So we'll start from the beginning. This is intended to be the plan view of a school bus. These guys here are seats. Not very many seats. If we put one student per seat, this is intended to be the head of a student. So we've got bums on seats. If all the seats are filled, then we say there are as many students as seats. I call this one-to-one correspondence in a here finite set. So this is correct. This will always work. Everybody agrees with this. Now, if the students are laying on the seats, so we've got here two seats, one student laying on the seat, then we can say we've got twice as many seats as students, and we could call that 2-to-1 correspondence. Everybody will agree with this on a finite set. And then we come to Galileo's idea. Here we have 1 compared with 1 squared, 4 compared with 4 squared. Galileo says because this correspondence occurs all the way to infinity, there must be exactly as many numbers as squares of numbers. This was around 1638. So he's claimed that since the table lists all natural numbers and all squares of natural numbers, it must work. And we've called this Galilean one-to-one correspondence for a very definite reason. We're saying Galilean here means false, bogus, invalid, historic, and basically worthless. Now, you've got to understand, Galileo's claim was supported by Cantor hundreds of years later, Dedekind, Hilbert, and crucially, every former student who's completed a degree in mathematics. That means everybody agrees with this. Any book you read will agree with this. Any teacher you speak to will agree with this. Any professor will agree with this. Anyone who disagrees with the standard mathematics is obviously an idiot. Quack. Don't know what they're talking about. So we're saying that infinite sets are not genuinely in one-to-one correspondence, and we're going to prove it. And we're calling this Galileo's Gaff. That's very unfair on Galileo. He had no chance of getting this right, but you'd get things like Galileo's paradox. Here we've got natural numbers. Here we've got squares of natural numbers. Amongst the set of natural numbers, the infinite set of natural numbers, almost no natural numbers are perfect squares. And yet, they're claimed to be in the same size, the sets are the same size. So that makes no sense. Galileo knew it made no sense. He said it made no sense. They call it Galileo's paradox. Really, it's Galileo's fallacy, because that isn't a way of counting. So, but the trouble is, nobody could figure out what was wrong with it. It looks as though it's correct. You follow along with the reasoning, nod your head, yeah, that must be true. And if you're a mathematician and you prize logic above everything else, if you can't find the error, you have to agree with it. And that's a bit of a problem. I mean, this is wrong. So, let's look at what it should really be. Now, this is a very stupid idea here. I've got the natural numbers. This is a double struck n. You'll notice on the diagonal, it's got 2 strokes. If I put the naturals on the top and the bottom, obviously they're both the same size set. It's the same set. Can't do anything else. But now I've got a little box. I'm saying that the 2 corresponds with the 2, the 4 corresponds with the 4, the 7 corresponds with the 7. Now, everybody will agree with this. This is perfectly standard. It agrees with everything everyone knows. I mean, we could reasonably disagree with that. But now, we're going to go a bit further than that. This box, because this box can be moved anywhere within the domain, so that's the domain is the natural numbers in this case. I can move this box wherever I like, and it always corresponds exactly. We're calling this translation invariance. It's a standard mathematical word or phrase. If you can move it along and nothing significant changes, I mean, we had a 2 with a 2, so we're taking the number and then we have the same number underneath. You can agree that wherever I put that box, even this way towards infinity, everything is hunky-dory. If we can't do that, then we have to hope that things go the right way, and we've shown examples where they don't. Now, suppose I cross out, remove completely the odd numbers. So I've got the set of evens compared to the naturals. Now, Galileo would have us believe that there are as many naturals as evens. And I say, well, look, here's my translationally invariant box. I've got 2 naturals for every single even. And that box can be moved to a similar position. So this is a similar position here, where you've got the even is on the right hand side of this little box. Okay, so that's translationally invariant across the entire domain. So the box is still translationally invariant. I'm saying that's correct. Not everyone will agree with me. Now let's look at that as a Galilean one-to-one correspondence. Now this is in a finite set, so I can understand a finite set. What I've done is I've shuffled these down to the left, and the empty spaces are left at the top of the set. So what happens if I do that with an infinite set? Well, I can keep increasing this 12. I can double it, double it, and double it until this is huge, and still half the set is missing. So basically, if you do Galilean one-to-one correspondence, you have to hide all these empty values off this way, off to infinity. And I'm saying that's not a valid way of doing things. You're trying to force correspondence where it doesn't work. So the red box works here, but it doesn't work here. And you have to kind of get your head around the idea that half the set is empty. So these are empty, but you know, you're halfway to infinity, whatever that means. So that's a tricky thing to get your head around. So we try not to do that. We say, is it translationally invariant across the whole set? And clearly it isn't, because this correspondence here fails at this end where we can't see it. So it's basically hidden. It's like you did your homework and the dog ate it. So, but nobody can see it. So that's not a good way of doing things. So we've got poor definitions, and here infinity is defined as being greater than any number. Well, who says that? Where did that come from? You see, we've got modern methods dealing with things, and saying that infinity, or that you can take a number and increase it and it at some point becomes infinite, is not in agreement with modern mathematics. If you remember advanced mathematics, there's the closure property of natural numbers. They're closed under addition. If you keep adding natural numbers to each other, you don't get infinity, ever. You always get a number. If you multiply natural numbers, you always get another natural number. They're closed under multiplication. Now, this concept didn't exist in Galileo's time. It didn't exist in Cantor's time. So they didn't have the ability to use these modern ideas. So they came up with some like mysticism. Oh, this infinity's too big to count to get anywhere near, and that's not true, because maths continues to work all the way up the number line. There's no point at which you say, it's infinite, I give up, maths doesn't work anymore. So you're not looking at this from the viewpoint of 1638 when Galileo looked at it. You're looking at it from later on when we had more understanding. So we don't want mystical nonsense from 1600s. Was a very difficult time. You start talking about infinity and people said, oh, that's God, we're going to have to kill you. You're talking heresy. So thankfully people don't do that anymore. You can come up with an idea and say, I don't agree with this stuff from Galileo, and you don't get murdered. So that's a good thing. So translational invariance and true n-to-m correspondence, they're given in a paper called Galileo's Gaff, which is mentioned at the end of the slideshow. Okay, so let's look at a genuine one-to-one correspondence in an infinite set. I've got odd numbers and even numbers. Now, there are definitely as many odd numbers and even numbers. So this correspondence here, again, this is translationally invariant. And actually nobody's going to disagree with this, because it agrees with the older view that you could basically put any infinite set in a table with another infinite set and they'll all agree, which is ridiculous, because it doesn't agree with the other measures that we have now. Now you see, Galileo didn't have the other measures. He didn't have the benefit of Cauchy. He didn't have the benefit of probability. So, it's very cruel to say, well, Galileo, you messed up. But Cantor, he did have, he was writing after Cauchy. He was writing after the probability of like dice games and things like that had been established. He really didn't have an excuse. And, modern authors, well, everybody has been accepting this stuff as, it's gospel. And frankly, it's considered so basic. You cover it in like 1 or 2 lectures at college, and it's just hammered out. And anyone who disagrees with it, well, they're basically an idiot. Because it's obvious. Obviously, it works. So if you try to challenge this obviously works stuff, well, you're a crank. Nobody would challenge this, because it's been stable for 150 years. So let's look at another one. This is 2 sets. Obviously, I've removed from this set here numbers that are divisible by 3, a mod 3 residue of 0. Here, this is 1 down from that. So this one's missing and this one's... So these 2 sets are the same size, and we've got translational invariance of this box. Now, I've got 3 boxes against 3 boxes, but there's actually only 2 numbers there. So we could call this 2 to 2 correspondence, because the sets are the same size. We wouldn't want to call it 3 to 3. And we certainly wouldn't want to call it 1 to 1, because this one here, that's a nice arrangement. This one here, so this is the same size. This is 1 more. And we come here, this is the same size. This one's 1 more. So this box is translationally invariant. And we can slide it anywhere in the range, anywhere this way, and it keeps going. Let's say the other way of doing it, where you hope that it works, well, that's correct and everyone will agree with that. This one, again, it is in a sense 1 to 1, so you've got 1 and 1, 1 and 1, but because the mapping is not constant between those two, it's better to call that 2 to 2. They're still the same size. So if we look at the naturals against that other set we were looking at, we can have 3 naturals and 2 from the other set, and then 3 naturals, 2 from the other set. So we still have translational invariance in that block, so that's all good. That's another block down here, but we could call it 3 to 2 correspondence. There's 3 here, 2 there, but also 2/3 of the naturals are in Y. The probability of randomly picking an element from Y is 2/3. So the probability measure, so that's the probability measure, which say Galileo didn't know anything about probability, that works. So we've now got a way of comparing the naturals. I mean, Galileo would say, and Cantor, that these 2 sets are the same size. And we say no, this set's smaller. It's got missing elements, and there's only 2/3 of them are in this set. If we asked what the probability of finding a value from set Y is if we randomly pick naturals, we get 2/3. So they agree. But when you do Galilean one-to-one correspondence, they don't agree. For example, Galileo and Cantor, they're saying that the evens and the naturals are the same size, same set size. In some sense, they get a bit vague because they know they're not telling the truth. They have to fudge some of the definitions. But if you pick a natural randomly, there's only a 50% chance that it's going to be even. And so the measure of probability telling you the size of the set and this correspondence method of finding the size of the set, they agree. But you don't need to consider the entire set all at once. I mean, you don't have to say the set's infinite and half of infinity is, I don't know, I can't really calculate the probability. You can just look in a small area, one of these translationally invariant boxes, and say there's 2 here and there's 3 there. So its probability is 2/3. That's very easy. So we've got a list of comparative measures of infinite set sizes. So the probability measure says, what's the probability that I'm going to pick from the naturals, I don't know, some value that's divisible by 3, for example. And you could say, well, okay, the probability of picking a number that's divisible by 3 is 1/3 if you're picking randomly from the naturals. Now, of course, it's hard to understand how you pick a natural from an infinite range. So that's a not too difficult problem to solve. But, you know, with picking a half, so if you're picking even numbers, it's pretty easy because you can say, well, we ignore the top half of the number. We just look at the last decimal digit. And if that's even, then the number's even. 3 doesn't quite work that way. But you can do the similar thing with 4, 5. But say 3 is a bit awkward. Now, the partial domain measure we've been using for quite a while. You take some finite limit, h, and you say, well, how many naturals are there up to h? And obviously there's h of them. How many of those are even? And the answer is h upon 2. Because the naturals have, you know, a repeating pattern, even, odd, and of course they go 1, 2, 3, 4, 5, 6, so 1 in 3 is divisible by 3, and so on. So those simple ratios, they work. And here we've got the ratio h upon 2 upon h. The h cancels, however big h is. And remember, h is not infinite so that I can't do maths with it. It's h is as large as you need it to be. Any value of h, remember, h is closed under, or the natural numbers are closed under multiplication. You can keep doubling h as much as you like. It never becomes infinite, and this ratio is a half regardless of the size of h. So that's really important. There's no concept that you ever get anywhere near infinity. You're just as large as you like. I mean, you can do mathematics on computers with the multi-precision integer library. I've done stuff with 10 million digits, 10 million decimal digits. I mean, it's ridiculously large numbers. And there's no point where they're even thinking that they're infinite. They're just ordinary numbers. Okay, they're a bit big, but... So we'll look at genuine n-to-m correspondence. Now, obviously, you can't compare two sets and say they're in one-to-one correspondence if they're different sizes. And this has always been a problem, that you have to bully people into accepting that the set of naturals is the same size as a set where you only have numbers that are divisible by 1,000,000. You'd say, well, it's 1,000,000 times smaller. No, it's the same size. Well, look, if you measure using the probability measure, the partial domain measure, the genuine n-to-m correspondence measure, all those measures give you the same answer. Whereas previously, this Galilean one-to-one correspondence was out on its own. You know, it didn't make sense. Galileo knew it didn't make sense, just couldn't figure it out. And he just didn't do his math properly. Now, obviously there are some sets that don't have a linear correspondence. You can't take h natural numbers generating h squared rational numbers and get a linear correspondence, because it's this business here. It's 1 over h. Only 1 in h natural numbers are perfect squares. And this is the idea that Galileo had, that these were actually the same. It's a ridiculous idea. But these are all valid measures of infinite set sizes. Now, so we've got infinite set sizes, we're comparing them in ratios, and that's a very easy thing to do. But if you start getting lots of infinite set sizes, it's boring comparing them in pairs. You get too many pairs. It's just boring. So you can instead compare them not as ratios, but you consider like what goes upstairs, what goes downstairs in a ratio. Now, in a finite set, so this is a finite set here, it's got 5 elements. So we're putting these bars around the set name, and that says there's 5 numbers in that set, 5 elements. Now, the natural numbers have a special symbol, the double struck n, which we mentioned earlier. So n, instead of natural numbers, some people start from 1, some people start from 0. You know, these are university textbooks, and they differ. The ellipses here, the 3 dots, just means carry on indefinitely. So you never stop. So we're defining the number of elements in that set as phi. Phi rhymes with I. There are phi natural numbers. And you say, oh, well, what does that mean? Well, I'm saying phi behaves as if it were a natural number. Now remember, we can never run out of natural numbers. There can't be a last natural number, and it never changes from being a natural number. You can keep adding, and it goes on forever. So it's infinite in that sense. It's infinite, but it's not using that, you know, that funny I8 on its side thing. It's long overdue that we don't use that. So we can just count directly. So size is a number. Cardinality, Cantor had to invent a whole new mathematics to cover up Galileo's errors. You know, I mean, he said, well, you know, we can't give it a number. It can't be a number because it's infinite. And it's like, okay, but we know numbers can't be infinite. I mean, it doesn't make any sense in terms of agreement. So we just take it as being a number. We don't know what the value is. It's just a number. But it means that if you treat it as a number, then you can divide it by 2, so that like the evens are half as big as the naturals. There are square root of phi perfect squares, phi squared rational numbers. You know, that all of mathematics of infinities are very simple. So I've written this all up in 2 papers. There's critical re-examination of the fundamental basis, and end-to-end correspondence is a measure of infinite set size. And it's this one which is mainly what this video is about. It's just an introduction. There's more examples in that paper, and there's a summary paper, The True Mathematics of Infinity, which is quite old in my years, and there's a little book as well, which is on Amazon. So you shouldn't write to me and say this disagrees with my textbooks, because obviously it does. Textbooks are wrong. The textbooks are going to take quite a while to catch up. See, if you're a professor of mathematics, you've been doing this for 30 years, you've got a lot of investment in this stuff. And you say, well, you read the first thing and say, oh, infinity is a number. And you've got, I know that infinity can't be a number. And you just turn off. You just don't even read it. Just throw it in the bin and say, this is rubbish, written by somebody who hasn't read anything. They should do my course for 10 years and then they'll begin to understand. Well, actually, this stuff is so simple that school kids can understand it. And you're basically poisoning the minds of youth. Corrupter of youth is what Cantor was called. And you can see why, because he just made things so that people got very confused. There's people jumping off buildings because they just don't understand how a set which has, well, there's almost no elements in it, and you say it's the same size as something else. You know, it makes no sense. But now, if you learn and understand Galileo's Gaff, you'll see where he went wrong and how to fix it. And it's very easy to fix. And I hope you understand it too.